Next up, we'll be having Louis, and he'll be speaking to us on a deep dive into JWT Algorithm Confusion.
Hey. Oh, wow. Hello, everyone. So my name is Louis. I'm basically used to be like a code reviewer, pen tester, AppSec person, and now I work for Pentester Lab. What we do is we teach people web hacking and code review, and we have fun. Basically, I love JWT, and today is Valentine's Day, so what a way to celebrate my love for JWT. I love JWT for a few reasons, and one of them is because it's a really good way to teach people how to hack and assign data, like protected data, and find a way around the signature without being a cryptographer. Because, full disclaimer, Yannick, I'm not a cryptographer. And that's why I like those so much, because you can hack crypto without being good at mathematics. So a lot of people use JWT, they use them for session, they use them for API call, they use them for to manage trust between services, they even use them for password reset. Often they use them because they need to have applications that work across multiple data centers, and they can't have like a shared database or a shared like NFS or something like that. So basically what they do is, instead of storing the data, they sign the data and they achieve the kind of the same level of trust. And so a few acronyms. So JOSE, JavaScript Object Signing and Encryption. Also the name of the working group, so basically the people who worked and put that amazing format together. JWT, so JSON Web Tokens, people call them JWT token as well. Do what you want. JWE, we're not going to cover that. Those are encrypted token. We only are going to talk about the next one, JSON Web Signature, the signed token. Then people also talk about JWK for JSON Web Key, and JWA, the JSON Web Algorithm, the algorithm used to sign the tokens. So we're going to get back. We're going to start really easy and hopefully go very hard. So follow. So encryption gives you confidentiality. If we simplify things, basically if you encrypt something, people will not be able to see what you encrypted. Signature, on the other hand, gives you integrity or authenticity. Basically, if I sign something, you cannot, someone cannot tamper with that information, either the information of the signature, without someone else being able to detect that. Here, we are only going to talk about signature. When you are signing information, you have two ways to do it, or two main ways to do it. HMAC, using a secret. So basically with HMAC, you do a construction on top of a hashing algorithm like MD5 or SHA-2, and you use that to create a signature with a big string like a secret. If you don't know the secret, you can't forge a valid signature. With asymmetric, with RSA or elliptic curve, for example, here we have two keys, and when you sign the data, you use a private key because no one else has the private key, so no one else can generate the same signature. When we are looking at, for example, two applications and they are using symmetric crypto, so HMAC, this is what happens. Both applications need to have the secret to verify and to sign the token. If we're using asymmetric, it's a bit smarter because only the service that is signing the data need to have access to the private key. Services that are verifying the data can rely on the public key, so they don't need to have access to the private key, so it's a little bit better security-wise. Now, the JWT format. So JWT format is based on JSON. I think everyone here has seen JSON before. And it's composed of three parts: the header, the payload, and the signature. These three parts are separated by a dot. So header, dot, payload, dot, signature. The two first parts, so the header and the payload, are base64 encoded JSON. This is why you can often see, if you see like JWT, this EYJ, because that's the base64 encoded version of a curly bracket and double quote. So that's going to give you this EYJ. The last part, the signature, is not JSON, so that's why you don't have the EYJ. So they are base64 encoded. That's not really true. They are URL safe base64 encoded without padding. Almost the same thing, but not quite the same thing. And for one good reason is that base64 encoded data doesn't play well with HTTP, because in base64 you have plus, which is a space in HTTP, and you have slash, which is a delimiter for path, so it's not great. So what they do is they use URL safe base64 encoding without padding. And what we do is we just base64 encodes the data, we remove the padding, so all the trailing equal sign, because that, again, is likely to break HTTP, because that's a delimiter between parameter, name, and value. Then we replace the plus by a dash and the slash by an underscore. And that's what URL safe base64 encoding without padding is. As part of the header, what is really interesting, and we're going to spend a lot of time on that, is we have the algorithm used to sign the token. So as part of this base64 JSON, we have this alg HS256 telling the service receiving that token, this token has been signed using HS256, which is HMAC with SHA-256. And basically, when you receive a token, you get that, and you say, like, okay, this is how I'm going to verify that token. And you have a lot of algorithms that are supported. You have the HMAC family, the non-algorithm, you probably have heard of, maybe not, maybe it's good fun. The RSA, the elliptic curve, and the PS family, which is RSA with different padding. Who here is familiar with the non-algorithm, to get an idea? A few people. So basically, as part of the RFC, they created this algorithm to sign the data, which is basically do not sign the data. And there was a lot of security issue because of that, because the libraries were trusting that algorithm, and you could just not sign your token and bypass everything. Also, for some reason, there is one Scala JWT library that supports HMAC with MD5, which is nowhere in the RFC, but they just decided to implement that. But it's only one library. So if you talk about algorithm, and we have, for example, the case of one client talking to multiple services, if you use HMAC and all the services are handling tokens, they all need to have the secret. So that's not great, because if one of your service get popped, the secret is basically everywhere. It's the same everywhere. So this service, or the person who popped that service, get access to the secret and then can forge secrets and can forge JWT. So basically, all the trust that you get from signing tokens, you'll lose it as soon as one of the services get compromised. When you're using asymmetric, you can either do the same thing and put the private and the public key everywhere, which is not great because you're not getting anything. But if you want to be a bit smarter about it, you can have one service with both the private and the public key, and other services with the public key. This is really good because if one of your services get compromised, they attackers only get access to the public key, so they cannot forge token. So security-wise, you get that's a really good thing. Obviously, people don't always do that because it's a little bit more compute intensive, and also it's a bit more complicated to deploy, and people don't want to bother. And you can even put your public key in the browser if you want to do for like a one-page app to do smart things based on the JWT. You can use the public key in the browser. So that's a lot better for deployment of like one-page apps. Now, after the header, what we got is a payload, which is basically where you put all the data you want to save, username, role, whatever you need to save about that token. So like, who does this token belong to? You also have claims, like expiry, issue at, not before, audience, GTI for claim ID, like a lot of claims that are supported by the libraries, and often people use them. So like, okay, I sign a token, I don't want that token to be valid forever, so I'm going to put an expiry on it. Because when you sign data, you don't want to sign data without an expiry. That's a really bad thing to do. But you have all these claims that are part of the body. So when you are creating a token, what you do is you have the header as a JSON blob, and you're going to JSON dump it as a string, and then you base64 encode that. Then you take the payload that is also JSON, you dump it as a string and base64 encode that. Then you concatenate with a dot the header and the payload. Then you sign the header and the payload using whatever signature mechanism you're using. Very important is people often think that only the payload is signed, but both the header and the payload are signed. Then once you got that signature, you base64 encode it, and you append a dot and the signature at the end to that to the header and the payload. That gives you your full token. What we are really interested in as an attacker is when the token gets verified, because that's when we want to do bad things. So what happens when a library or an application is verifying token, it first splits the token in 3 parts based on the dots: header, payload, signature. Then it's going to base64 decode each part. Then it's going to parse the JSON for the header, because we need to know what algorithm was used to sign the token. Once we parse the JSON, we can retrieve the algorithm from the header. And so this is just getting the algorithm, and then we have the algorithm, we have our secret or public key, and we can use that to verify the token. And finally, we can verify the claims to make sure, for example, that the token hasn't expired. If you're into crypto engineering, that's a lot of steps before the signature gets verified. So that's basically the danger zone. Everything in that part happens before the signature is verified. So everything can go wrong. And it hopefully will during the demo today. So when you attack JWT, you put your black hat or bad guy's hat on. Your main goal is to find ways around the signature mechanism. And that's what we're going to look. There are many ways to do that. If people use a dumb secret, that's going to be a good way because you can crack it offline. If the library supports the non-algorithm, you can use that to bypass the signature mechanism. You have injection in the key ID, which is an element of the header. You can also inject in the JKU and X5U via SSRF. But today we are going to look at only one thing: algorithm confusion, because it's, as a name, the name doesn't come from it, but it's pretty confusing. Everything good until now? That's when the suffering starts. I'm not joking. It's going to be fun. So I said multiple times, the application or the library will use the algorithm from the header. We all happy with that? Because that matters a lot. That's a lot of text. So basically, when you're sending a token, the token is going to say okay, the service receiving the token is going to say, okay, this token was signed with HMAC because this is in the header. Or this token was signed with RSA because it's in the header. Now, what happens if I'm being a bit naughty and I say okay, this token is signed with HMAC even if you are expecting RSA? What may happen? So when you sign with, when you use RSA, again, you sign with the private key and you verify with the public key. When you sign with HMAC, you sign and verify with the same key. So if I'm a developer, this is what the code will look like. I'm going to call my library, say JWT, verify, token, and public key, because I'm using RSA, right? So that's the code written by the developer in the little blue box. And in my head, I'm thinking, okay, this algorithm here is going to be RSA, right? Because my application is using RSA, and I've never used HMAC of my life. I hate HMAC. I'm a RSA person, not the company's algorithm. So that's what developers think is happening, because they're verifying a token with the public key. So surely, and they're signing the token with RSA. So surely, when they receive a token and verify it, it's RSA again, right? But what is really happening is that this algorithm is controlled by the header, is in the header. So it's controlled by the attacker, sorry. And again, this happens in the danger zone before the signature is verified. So what if I'm being an attacker and say okay, instead of using RSA, you're going to use HMAC. And this is basically what algorithm confusion is as an attacker, I'm going to say, we're not using RSA anymore, we're using HMAC. Because HMAC is cooler. Let's reuse it. And if we look at the code written by the developer, it's still doing verify, the token, and the public key. And the public key is kind of public, right? So how public is the public key? So you can find the public key in JavaScript or front-end code. That's good. You can reverse a mobile client like an Android app or an iOS app and get the public key. That's cool. You can find it in the documentation if you're very lucky. But what you can also do is you can recover the public keys. So have you heard about Bitcoin? Yeah. So when you send money to someone using Bitcoin, there is a sender and a receiver. In the Bitcoin transaction, there is no receiver address. There is no sender address, sorry. The sender address is computed based on the signature. That's something you can do with ECDSA. Based on the signature, you can recover 2 potential public keys. And that's how Bitcoin and like most blockchain, as far as I know, do it. It's like, okay, we have a signature. From that, we can compute a public key. And then there is a bit, because, you can compute 2 public keys, sorry. And from that, there is a bit saying like, oh, that's the odd or the even one. And that's how you know, as when you look at a Bitcoin transaction, who actually sent the money. This is based on the signature. There is no like sender address or something like that in the transaction. It's all based on the signature. If you're using RSA, someone way smarter than me wrote like a little tool to do that, to go from a few signatures to a public key. So if it's elliptic curve, 1 signature, 2 public keys. If it's RSA, 2 signature, 1 public key. So this is how you recover it in Python. It's a lot of Python. It's yeah. And yeah, basically we get the token, we split it in 3 parts. We base64 decode the signature to get like the last part to get the signature, what we got from here. Then we do like a bit of massage of the signature to make it right. And then we call this method named sig recover public key, because most ECDSA libraries have a way to recover a public key from a signature, because that's what all like crypto, like blockchains are doing. So it's completely legit. So you don't even need to know how to do that. Most ECDSA libraries have a way to do it. Then what we do is we modify your token, say like, okay, instead of using elliptic curve, we're going to use HMAC with HS256. Now we change our username to admin, because it's cool to do like an attack, but if it stays the same user, it doesn't really make sense. So you want to become another user. And then we use the public key, so the 2 keys we recovered, and generate tokens, and then we try the tokens. So that's how you do it with ECDSA. So let's do it. So what we're going to do is, first we're going to pray a little bit. So we have one application, that should be this one. So we are currently logged in as a hacker. What we do is, this is just a cookie with our JWT, so we're going to take it here. We copy it here. Oh, sorry, that's... Oh, I can show that later, actually. No, that's not here. Yeah. Okay, so we are hacking ECDSA here. So we have a bit of Ruby this time, but it's exactly the same thing. The ECDSA library in Ruby has a method to recover public key, because that's part of ECDSA. That's something completely normal. So this code is just basically recovering the public key, and the half of the work writing that code was just like finding the right way to put that together in a PEM, in the public key format. So what we do is we do ruby exploit.rb, we put our token, and we end up with 2 public keys in PEM format. And then those public keys are just used here to compute an HMAC. Very, very simple. Then we take one of the 2. First one or second one? 2. I think you're not lucky. You got 1 chance out of 2. Then we get the cookie here. So let's show that. So we still hacker. we put the new token, we reload, and we're not logged in anymore because the verification failed. I'm blaming you. So we're going to try the first one. We passed it here. I reload. And yeah, we are currently logged in as admin. So basically, just by getting a token signed with ECDSA, computing the public key, signing the message back with HMAC and saying like, oh, actually, this is no longer elliptic curve, this is HMAC, we can say to the application, we are another user. Now, if we want to do exactly the same thing with RSA, we're going to do the same thing, get a token signed with RSA, recover the public key, get multiple tokens, actually. Decode the header and change the algorithm from RSA to HMAC, and then tamper with the payload to say we are someone else. So there is this amazing tool. So ECDSA is done. Yeah. So we are. So this is just a tool from GitHub. So this time we take the token from here. We are logged in. Yeah. So this is one saying we are hacker. Then we're going to take another one. For example, we can log out, and I think I got a test account as well. Okay. We take the other token. We paste it here. That's going to compute that's going to compute N and E to recover the public key, and from actually. Oh, shouldn't have done that. I'm going to regret it. I'm going to come back to that. So basically the problem here, I try to kill it because the current script doesn't change the username. So I'm going to stay the same user. So it's a bit boring. So see, insert hacking here. Now we can do the hacking. So it's going to take a few seconds, hopefully. I'm on battery to make things even more fun. But hopefully, we should quickly get a JWT. So with this tool, we're going to get two JWT, actually. We're going to get one key, but in two formats. So one is going to be in X509, and one is going to be in PKCS1. Yeah, that worked. First one or second one? First one, they are printed here. We reload. Yeah. So everyone understand JSON Web Algorithm Confusion attacks now? Yeah. Sorry. You try to kill me? Because it's trying, so it's brute forcing the key. It's brute forcing, yeah. The other one is just basic computation for ECDSA, but like for RSA, you need to brute force the key and try to find, you know, as part of RSA, you got E and N, you need to brute force N, and then it's easy done. Oh, yeah. So now we're going to look at how libraries prevent algorithm confusions. Yeah. Yes. Yeah. I need valid tokens to be able to get the public key. If I don't have any valid to recover it, yeah. I need to be logged in. If I don't have any tokens, I can't do the attack. I need at least one token for elliptic curve and two tokens for RSA. Now, I'm a strong believer that to get really good at code review, you need to look at a lot of source code. So that's what we're going to do. Because if you do code review, the better you understand how attacks are blocked, the faster you can dismiss hypotheses during code review. Also, the better you get at recognizing like bad patterns or things that are almost right and things that are worth investigating. And also, it's really good for deliberate practice. Like, you know, a chess player, they do like deliberate practice to get better. That's the same thing. You keep reading code until you cry, and then you get better at code review. Trust me, it works. Also, I may be a nerd, disclaimer. So one way to block algorithm confusion is to not support RSA and elliptic curve. Basically, if you don't support those, you're never going to have the issue. And you have like a few libraries on JWT.io where like all the JWT libraries are shared with everyone, but just support HMAC. So no elliptic curve, no RSA, no problem. But you kind of want RSA or ECDSA. But keep it simple, stupid, usually works. Another way is, you know how I say like library trust the algorithm coming from the token. What you can do is just ask developer using your libraries to set an algorithm, to say like, we are only going to support this type of tokens. And then you match that. You say like, okay, as a library, the developer told me we're only using RSA. This is an HMAC token. I'm not going to support that. I'm just going to throw an exception. So this is what they are doing here. Don't remember the code base, but that's Ruby, so that's probably good. Oh no, actually, that's not Ruby. Yeah. Oh, that's Ruby, but some code. Sorry, that's Ruby, but some code is missing. Okay, so here we see that they get the algorithm from the header and they validate it against the algorithm provided by the library. Another way to do that, to prevent algorithm confusion is just to ask developers using the library to provide an algorithm and then completely ignore the one in the token. So like, okay, the developer of the application told me they want to use RSA. We are going to use RSA regardless of what is in the token. We just don't care. That's what they're doing here. They basically, okay, they ask the algorithm, they get the algorithm from when people use their library, and they say, okay, get algorithm data from the algorithm, and they don't use the header at all. Another way to do that as well is to use both strategies, ask for an algorithm, then validate that it's the same. If it's not the same, I throw an exception. And then on top of that, I don't even trust the one coming from the token. I use the one provided by the developer. Good way to block that attack. That's what they're doing here. They're verifying the algorithm, and then they use the algorithm provided by the developers, not by the token. Defense in depth, always good in security. Another one that is not as good, that's in PyJWT. What they try to do is look at the secret used to sign with HMAC and see if it looks like a public key. And if it looks like a public key, they throw an exception, saying like, oh, someone is trying to attack us with algorithm confusion. And so that's what the code is doing, is PUM format or is SSH key. And they have this big regular expression. And it's pretty risky because if you mess up your regular expression, or if you forget something, things go wrong. And when things can go wrong, they usually go. So that they had the CV in 2022 with exactly that problem, is that I think they forgot, they had begin public key, but they didn't have begin RSA public key. So that was a bypass at the time. Or they were missing as well begin EC public key. So at the end, what they end up doing is say like, oh, we need developers using our library to set the algorithm. And also like, what if my HMAC secret is begin RSA public key? That's going to break the application, so I can't do that. Yeah. Another way to prevent those kind of attacks is to rely on the type of the secret or the key and say like, okay, here we have some Java is Lava. We check that the key is an instance of secret key because we are signing with HMAC. Secret key is what Java used to store HMAC secret. If it's not an instance of secret key, we throw an exception because we can't sign with anything else. That works pretty well as well. Same thing in PHP. This is Web Dev Cave JWT-PHP. They validate the secret, and in that validate secret, they check that the secret is either a HS secret or RS secret. And for HMAC, you need a HS secret, and for RSA, you need a RS secret. Very simple. Another one I came across is trying to do auto detection based on the variable type, saying like, okay, this secret or this data we got to verify is either a public key or a private key. So we're going to look at the type of the value of the variable and then use that to decide what kind of algorithm we are using. What is interesting here is that that library is only doing it for signing, they're not doing it for verifying, unfortunately. For verifying, they just don't care. They take the private key or the secret, and when it's HMAC, they use, again, this private key or secret, and they do a HMAC digest of digest the secret and signature-based string, so header plus payload. And what is very interesting is that I had to test that because that looks really very much like it will be vulnerable to algorithm confusion, so I had to run like some tests. And what is happening when you do that is that the code is almost vulnerable, and the only thing that is preventing this from being exploitable is the fact that OpenSSL HMAC digest in Ruby doesn't know how to compute an HMAC of a public key. So this OpenSSL HMAC digest knows how to deal with strings, but it doesn't know how to deal with public keys. So that creates an exception, and that doesn't work. I was very sad. That's my face. But wait, there is more. So when looking at those protections, when trying to get better at doing code review on JWT algorithm confusion, as you do, I didn't want to look into Java because I have looked at enough Java in my life and I try to avoid it as much as possible. So I decided to look at some Scala. Not a great idea. And one of them seems interesting, but it wasn't maintained on, like the GitHub project wasn't maintained, but still listed on JWT.io. And I think that's a great exercise because let's see how, like, looking at what is preventing something from being vulnerable really helps us quickly discover vulnerabilities. Let's find a bug. So this is a library, and this is how you use it. You say JWT.decode the token and your super fancy secret. That's the name of the library. First red flag, you don't need to provide an algorithm. As a developer using the library, you don't need to provide an algorithm. Okay. Then we look at the decoding. They split into 3 parts. They check that there are only 3 parts. They split on a dot and they check there are only 3 parts. They get the header, payload, blah, 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 blah. Then they call this get algorithm from header. The library relies on the header. So again, good sign that things will go wrong. Then we keep going, we look at the validation, they get the public key, and here we see that when they validate using get the public key, they take the public key as a string, and the secret as a string, and the public key as a string. So when you want to verify with that library, you need to provide a string. You don't provide a public key object, you provide a string, which is a really good sign that the code will work with HMAC. So quickly, you take the code base, you generate your little POC, you're using public key, you're using the public key, you encode using RSA to just create a valid token to see that everything is working. Before testing the attack, you want to make sure that the library actually works, and you generate a token. Then you have your verified token. The verified token takes the public key, blah, 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 that's a Scala code. And then either you have a success or a failure in the Scala code, depending on how the decoding, if the decoding works or fail. Then you forge your little token. It's just a token, like you create a normal token signed with RSA to make sure that everything works. Then you generate another token manually using HMAC and HMAC of the public key for signature. You run that code, and both tokens get decoded. You don't get a failure. Big success, you found a bug. You're very happy, you go on GitHub, you contact the person, you're like, okay, I found a vulnerability, blah, 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 in your application. So I contact them to say like, oh, I can share information with them. And that was the 3rd of October, and I'm still waiting. But the fun of open source disclosure, again, my face. But wait, there is more. So I did like a similar talk in Poland. No, sorry. So that the first one I to find was bug on a plane back to Poland. I felt like I would never find this kind of bug. But then I did that talk again closer to where I live in Brisbane, near Brisbane, and I was talking to a friend. I was telling them like, okay, I found one algorithm confusion. There is no way I'm going to find another, especially since I'm running out of good libraries in like weakly typed language. So I'm like, I'm never going to find another one. And so I was in the Assumption Club. So I think we all know why we're here. So assumption insecurity, really bad, don't do that. And I start looking at a few C libraries, and including this one named CJWT. And I start looking at the code, and that's, I got plenty, oh, cool, I'm going well, time-wise. So looking at the example, because that's a good way to see like how people use the library, and that's the example. So we have the public key here as a big string, and then we have the code used to decode a token. First red flag, the public key is provided as a string. That may be vulnerable. And then developer using the library don't need to pick an algorithm. So another red flag. Then I looked at the HMAC version of the same code, and the code is exactly the same, except instead of having a public key here as a pointer to a char, here it's actually the secret. So it's exactly the same code. So if you have been listening, yeah, it's probably going to be vulnerable, right? And yes, because the code are exactly the same. So it's likely that since we don't provide an algorithm, that's going to be the same issue. So that's the code of the verifying the signature. And we can see that in the switch statement here, they basically use the JWT header algorithm to decide how they're going to verify the token. So here, if we tell them it's HS256, they're going to use HS256. And I put like a little Ruby poke together to create the right token because it's a little bit easier. A good way to do that is using the public key from the documentation, from the example. So this way, developers, when you report the bug, they know how to reproduce it pretty quickly. Then I wrote some C. Then I got ChatGPT to write some C for me. I'm being honest. So basically, like doing the same thing, like verifying a token, but instead of using a token signed with RSA, using my malicious token signed with HMAC and the public key. And it worked again. And I reported the bug on the 4th of December. It was fixed on the 18th of December, and advisory published on the 19th of December. So like really, really good job from the developer. You don't see that every day. Yeah, and I was very surprised to find this kind of bug in a C library, but yeah. Conclusion. So recommendation for JWT, review the libraries you pick. Try to find libraries that are pretty simple because otherwise it's going to be like really hard to audit. Make sure you check the signature because algorithm confusion are really cool attacks. Cryptographically speaking, they are interesting, but most of the time people just don't verify their token. So like this is hard to do. This is annoying to do. But most of the time, you just like change the payload and people don't verify their token. So if you're using JWT, make sure you check the signature. Make sure you even have automation to check the signature on your services on a regular basis. So you get like a cron that runs every day and try to send a token that is unsigned. And if it works, you're like, okay, throw an alert, send me an email or something like that. Make sure your tokens expire. If you sign data, you don't want the signature to be valid forever, because that's a really, really, really bad idea. Someone can come back in 20 years with a signed token and you still think it's valid. And then enforce the algorithm. If you're using JWT, make sure when you're using a library, you can tell to the library, this is the only algorithm we are supporting. Because if you do that, you're going to kill this kind of shenanigans, and you're going to kill also the non-algorithm attack. So enforce the algorithm. Like, don't use libraries that don't force developers to not enforce the algorithm. Yeah, so if we look back at algorithm confusion, enforcing the algorithm or relying on the type are clear winning strategy. If you like code review, reviewing multiple libraries at doing the same thing is really good, because instead of being smart and having to know everything to check, you just spot the difference. Are they doing the same thing? Is something missing? That's a really good way to get better at code review. And then once you have reviewed a lot of libraries, even if you don't find any bugs, this is not time wasted. People think that when they do code review and don't find any bugs, they wasted their time. That's not true. If you do code review, you get better at reviewing code, and then it's really easy to spot bugs when there are bugs to be found. And code review is fun, trust me. If you want to be like LinkedIn friend, B-Sky friend, or whatever, just like, I'm pretty friendly on the internet. I love to talk about JWT, as you probably can tell. And otherwise, yeah, thanks for your time. Oh, yeah. I brought a silly amount of swag, and I don't want to bring it back to Australia. So if you want to grab something, t-shirts, stickers, keyring, whatever, just come and I will hook you up. And thanks a lot for your time and your attention. And if you have any question, please don't hesitate. Oh, sorry. Yep.
Yeah, I feel like a lot of it came down to the library correctly. What can we learn about a secure API design to make sure that developers don't shoot developers?
In general for JWT? Just for JWT?
Generally speaking, you have to move on good API design so that this doesn't happen again. It's pretty bad.
Keep it simple. Something named Pokayoke, like basically error proofing your API. So make sure that developers can't get it wrong. So there is one way to do things. Using the same libraries everywhere, so you only have one to review instead of like every developer using their own libraries. Trying to get every developer to use the same language, or having like a process to introduce new languages for development, because if you have 20 languages, it's really hard to do AppSec really well. Having unit tests, so when you have these kind of things, you have unit tests to test for those. I can go for hours. Thank you. Any other question? Yeah. Yeah, so basically when you use, what you do is if you have strong typing for the data, and the library is expecting a public key, and you provide a string, or if you are, the application is actually the other way around. If the application is expecting, the library is expecting a public key, not a string, and you provide a public key, it will throw an exception. Because it's going to try to use the public key as a string for the HMAC, and that's going to throw an exception, because it doesn't know how to do an HMAC with a public key, because you should never do an HMAC of a public key. You should do an HMAC of a secret or a string or something like that. A public key object. Like could be a byte, in memory could be most likely a byte stream, but most like should be like a public key object or something like that. Any other question? No. Oh. No. Should I?
I don't know. I just was playing with the Hack the Box box a couple months ago, and there was a JWT Algorithm thing, and it wasn't too hard, but I had to learn a bunch of stuff. So
Cool.
I should say it was a learning one, but it's Blazor stores a heck of a lot more belong on the computer, and so for me, that JWT just in general, it seems like a really right target area.
It is, and it's a lot of fun. Like you can this is just one part of it, going in deep dive, but you can you have so many ways to hack JWTs. So many ways. None.
The best part about Blazor is you actually get DLLs get downloaded to your computer, so you can actually look through their code.
Okay. Cool. Right.
I think it's the best part.
Okay. Okay. Thanks for your time.